Today we are going with unit number 4 revision session, that is about network layer. So here, first of all, we will discuss what is network layer. Okay, so here network layer is, we can say network layer is the layer 3 of OSI model, which is responsible for delivering packet from the source host to the destination host across one or more interconnected network. Okay, so already we have seen this image, already we have learned when we started with OSI model. We know that there are total 7 layers, and if it is from sender to receiver point of view, if we talk about that, the first layer we consider it as application layer, and from receiver to sender point of view, the physical layer will be the first one. So here we can say that what actually this network layer, what is the function of network layer, right? So we can say it receives segments from the transport layer, encapsulate them into packets with logical address, and then rely on the data link layer to deliver those packet over individual links. Okay, so again I'm repeating, when we are talking about sender to receiver, here the when it comes to sender to receiver, it is layer number 3. Okay, and both area, because both area it is yeah, sender to receiver it is 3, and obviously it is from receiver to sender also, it gives third layer only. Okay, so here we are moving with the next option, that is why it is, the network layer is also called internet layer or IP layer. Now why it is called so? So we can say that it performs communication between different networks, which is the main function of the internet. So here in IP, TCP IP, this layer is also known as internet layer because it enables internetworking. And it is also called IP layer because it primarily uses the internet protocol for addressing and routing. Okay, now what are the main responsibilities of internet layer or IP layer? Or else if we talk about OSI model, what is the responsibility of network layer? So the first one is logical addressing, second is routing, third is packet forwarding. Okay, so what is logical addressing? So we can say that logical addressing gives importance to assigning unique IP addresses to the device, and also it will identify the source and destination in the communication. When it comes to routing, we can say that it chooses the best path for data packet to travel across multiple network, and also it uses routing algorithms to decide the path. When it comes to packet forwarding, we can say it moves packets from one router to another, and also it ensures packet reach the final destination even across many networks. Now, the protocols which are majorly we have seen in network layers are IPv4, IPv6, ICMP, IPsec, etc. are the major protocols that use. What are they? We can say that network layer design issues faces two major issues. The first one is what service to provide to the transport layer. Okay, whether it is connection oriented or connectionless. Now, how to design the internal network like routing, switching, or congestion control, all this network internal network issues, how it can be solved, right? So here one image we have added, which is having two hosts, one is host 1 and host 2. So here host 1 is sending some process to host 2, and here one router, customer routers are there, that is the F is customer router, and the remaining which is there in ISP network, we can say these all are the different routers which are actually sending the packets to the next node. Okay, so here we can say A, B, C, D, E and F. These are the different routers which are connected to host 1 to host 2. Okay, which is connected in between host 1 to host 2. So here when the packet, this is the packet which is actually coming from host 1, okay, and it is moving to it is moving through the router, which is actually A to C, we can say, or else it can go to, after C it can go to D, then after E and F, accordingly it is reaching to the final host, we can say like that, or else whichever is the shortest path it select accordingly and it move the packet. So here we can say the host 1 and host 2 are there. ISP network is there, that is A, B, C, D, E. These are interconnected network, and F, that is a customer router, but it still work exactly as ISP router. Each router uses store and forward switching, okay, and it shows the entire environment where the network layer works, okay. So here the host create the packet, a router forward the packet, ISP router forms a mesh of a path, customer router behave like a ISP router, and packet travel hop by hop using store and forward switching, and finally it reaches to the destination. So this is the way the network layer works. Now, when it comes to service provided to transport layer, already we said that in the starting portion only, the network layer, it is located below, above the data link layer and below the transport layer, that is between two and second and fourth layer, right? So here what are the services that are provided to the transport layer? So the network layer provides service to the transport layer in the form of service must not depend on router technology. So here this is the first service. Second is transport layer should be aware of number and the type of routers, and third we can say uniform addressing, right? So these are the major three services. Now what are they? Okay, right. So here service must not depend on router technology means router may be from different companies or different hardwares, right? So here the transport layer should work the same regardless of router types. So this is point number one. Second is transport layer should be unaware of numbers and type of router. So here what is happening, the transport layer should not care how many routers exist or how they are connected. So here the router must hide or it will abstract the internal details. When it comes to uniform addressing, the network layer should provide one consistent addressing scheme across the LAN or WAN. So here the example we can say the IP addresses works everywhere, right? Now the next topic is routing protocol. So here routing protocols are the rules and procedures that routers uses to exchange routing information, learn available routers or learn available routes, then maintain routing table and choose the best path for forwarding packet in a network. So here routing protocols are essential for enabling communication across large dynamic network where routes may change due to link failure, congestions or topology changes. So again, we can say that routing protocol means it is a decision making process that select which path a packet should take. So there is routing protocol involves or it includes to choose the best route, to maintain routing or routing table and update routes where the network change. So here the features of routing protocols, we can say discover all available paths. Second, determine how many paths exist between source and destination. And the third one is select the fastest or the best path. So when it comes to the first feature, that is discover all the possible path, we can say routing protocol automatically detect newly added router, new networks and the available links. So this is done by using the hello message, broadcast, multicast, neighbor discovery mechanism. The router builds a complete view of this domain. Okay. And when it comes to determining how many paths exist between the source and destination, we can say that if multiple paths exist, this routing table will store them in a routing table, mark each path with a matrix, that is its cost, hop count, then bandwidth, its delay, etc. And having multiple paths will improve the redundancy, load balancing, and reliability. So again, I'm repeating here, the routing protocol means it is a rule or a procedure that the router uses to exchange routing information. It learn available routes or available routes, maintain routing table, and choose the best path for forward packet in a network. Okay, so what is happening by using this routing protocol, what benefit we are getting? We can say that it may change it, or it may reduce the failures, it may reduce the congestions what is happening in between when information or when the packets are sending from source to destination. Okay, for that purpose we are using this routing protocol. So it will choose the best route, it will maintain the routing table, and it will update the routes when the network changes. Okay, now what again the third feature is, as we said, it will select the best or fastest path. So the best path is selected based on the routing metrics such as hop count, bandwidth, delay or reliability, load, cost, maximum transmission unit, administrative distance, and each protocol uses its own method. So here the major protocols which we are using for these purposes are RIP, that is routing information protocol, which is giving importance to hop count. Second is open shortest path first, that is short path first, SPF. Then after, enhanced interior gateway routing protocol, which is a composite matrix which was having bandwidth plus delay plus load plus reliability. Okay, so here the major point that we have to remember when it comes to routing protocol is what is routing protocol, what are the features of routing protocol. Okay, and the next is what should routing optimize, that is also a very important question, right? So here we can say that it will optimize the, or it will minimize mean packet delay, it will maximize the network throughput, it will reduce the number of hops and reduce total distance traveled. So however, this high throughput often means long queue, which increases the delay, and reducing hopes helps improving both throughput and the delay. Okay, so here already we said that actually it works in metrics also, right? It is having some matrices to calculate the shortest path. So how it is actually giving importance, or what are the things? So again I'm telling, on that point itself we said that it gives importance to hop count, bandwidth, delay, load, and reliability, right? Or else we can say there the points which we have discussed are hop count, bandwidth, delay, reliability, load, cost, maximum transmission unit, administrative distance. Each protocol each protocol uses its own method, right? Now, when it comes to types of routing algorithms are divided into two broad categories, that is non-adaptive routing and adaptive routing. So here non-adaptive routing is also known as static routing. So here it does not change the selected routing decision for transferring data packet from source to destination. They construct a static routing table in advance to determine the path through which packets are to be sent. So here we can say the static routing table is constructed based upon the routing information stored in the router when the router is booted up. Once the static paths are available to all the routers, they transmit the data packets along these paths. The changing network topology and traffic condition does not affect the routing decisions because it actually giving importance to non-adaptive method or static routing. Okay, so here that again the points which is very important when it comes to non-adaptive routing. The first is routing decisions are fixed and do not change even if the network condition change, right? So here in non-adaptive routing, once a route is or once the route is selected, that is A to B, B to C and C to D, this path remains unchanged. It does not react to congestion, link failure, router failure, new nodes added, traffic variations, etc. Because the routing algorithm does not monitor the network state, there is no mechanism to dynamically recompute the path. Okay. Second is routes are pre-calculated. As we said, it is static routing method. So we can say routes are pre-calculated and manually configured. So here paths are calculated beforehand by network administrator or the algorithm designer. They are installed into routers routing table statically. The router simply look up the table and forward the packet. So the characteristics of this area is, or this approach, we can say no runtime computation required. Router does not run any complex algorithm. It is easy to configure in small networks also. Then the third one is no router exchange information. Means here we can say no routing updates, no hello messages. Okay, there is no vector designs. Okay, and when it comes to route also, we can say router does not communicate to share the link status, distance, congestion levels, topology changes, etc. Now, why this no router exchange information, this concept is actually matter, or why it is needed? So we can say because of that no traffic, no control. Traffic means over low overhead, and also we can say no knowledge of changes, zero adaptability is there. Okay, so here again, no router exchange information means no routing updates, no hello messages, or no link state advertisements, no distance vectors. Okay, and it does not do not communicate to share all these status or distance or level or topology changes. Okay, now next is we can say it do not adapt to failure, congestion or topology changes. That was the fourth point. So since there is no updates, no monitoring, the router cannot detect the broken links, right? Because in the previous feature only, the previous area only, we said that router do not communicate. It do not communicate to share link status, distance, congestion level or topology change. So here we can say since there is no update or no monitoring, so the router cannot detect the broken links, router down, new route available and overload paths. Okay, so what happened as it is there is no updates or no monitoring, and also it does not detect all these things. So what happens, we can say the packet continue to send on the same path. If link fail, packets are dropped, and if congestion increases, still use the same path. So here what is happening, we can understand again with an example. If a link, okay, if a link B send any information to C, here it is actually giving importance to static routing. So static routing will still send packet towards C, causes packet loss. Means when the information is sending continuously, there is no information about broken links or the router down or the new route available, whatever the problems are there, accordingly what is happening, it actually lost the packets. Now, fifth one is simple and less overhead, we said. So, the meaning is no CPU needed for recalculating the routes, no memory needed for the topology database, no bandwidth used for routing updates. Configuration is straightforward, right? Because in the first point itself, we said, first or second point, we said routes are pre-calculated and manually configured. So, here you can see that IP route or IP route 10.0 point approximate the values are given here, right? Accordingly, the IP was configured. Okay, the static route was configured here. So here we can say simple and simple and less overhead means here we were discussing that no configuration is straightforward. So that is the way it was actually configured. It was configuring the IP in a manual form. Very fast lookups and idle for very stable networks. Again, I am reminding we are talking about static routing. So that is the reason that it is actually very fast and it is idle for very stable network. Okay, so again, if we talk the opposite or the negative shade, we can say it is not suitable for the large or frequently changing networks. Okay, so here the example again, we can say the shortest path routing algorithm, fixed routing and flooding are the example for non-adaptive routing. Okay, here you can say Dijkstra's algorithm or Dijkstra's algorithm or Bellman-Ford algorithm can be considered for shortest path routing. Okay, here the next one is, as we were talking about adaptive non-adaptive routing, now the second one is adaptive routing. So again, I'm giving 30 seconds you to please understand the concept. Please revise whatever we have learned here. Okay, the first thing is about what is the routing, features of routing. Okay, three features we have discussed. Then after we said why, what should routing optimize. Then after, what are the matrices in routing, what are the types of routing. Okay, there are two types of routing, non-adaptive and adaptive. Non-adaptive means it is a statical one, and adaptive routing we are going to learn about that. So here when it comes to non-adaptive, we said that does not change the selected routing decision for transferring data packet from source to destination, and they construct a static routing table in advance to determine the path through which packets are to be sent. Okay, then after we have discussed the features, okay, or the type in non-adaptive routing, what are the different features that we have to understand, right? Or what are the features over here. So the first one is routing decisions are fixed and do not change even if network condition change. Second is routes are pre-calculated and manually configured. Third are no router exchange information. Fourth, do not adapt to failure, congestion or topology change. Fifth one is simple and less overhead. Now when it comes to adaptive routing, an adaptive routing technology is also called dynamic routing. In this algorithm, the routing decisions are made based on network traffic and the topology. So the parameters that are used in adaptive routing algorithms are distance, hope, estimated transmitted time and count. So here the examples are RIP, OSPF, EIGRP and BGP. These are the different protocols which are used. Okay. Now here adaptive routing, again we can summarize it as like, it's like it refers to the routing algorithm where the routes or where the routes automatically change whenever the network condition change. In static it was not possible. Whatever the conditions are there, it will be, the network condition will be same only. And here it is based on the we can say the routing algorithm where routes change automatically. Accordingly the network condition also will change, or according to the network condition the routes change, right? So here it will include the congestion on the links, link failure, changes in network topology, increased delay, addition of new routers. Okay, so these are the area where the we can say where the routes or where the routes are recalculated. Okay, or routes are reallocated. Now when it comes to the features of adaptive routing, routing decision change automatically based on the network condition. So here in adaptive routing, router monitor the network continuously and update their routing table as soon as change is detected. Okay, the changes can be link failure, congestion, new routers or removed routers, better or short path becoming the availability. So by exchanging this routing information and it will recalculate the best path. Okay, so here again, whatever the 5 points we have learned in non-adaptive, that all are here also with some more features. Okay, with some more features. So here in non-adaptive we said that the network condition will not change, but here depends on the routing decision, it will automatically change. That is the first point. Okay, now here the example is if I want to send any information to A to C, so A to B then C, this is the way we are sending the information. What happened if the router A, or if the information A to C fails, then the router A will immediately switch that, it will move the information or it will exchange the information through A to D and then C without manual interventions. Okay, now second is router exchange informations regularly. Okay, so here adaptive routing protocol keeps the network update by sharing information such as link status, distance metrics, bandwidth, delays, hop count, and topology updates. So types of exchange informations are direct vectors, then link state advertisements, topology chains, and path vector. So without regular exchange, router cannot know about the failure or new routes, right, or new routes. Now here the next one, third important point is it adjusts the routes dynamically. Okay, so the routers recalculate whenever the network goes down, then the links goes down, the links comes up, congestion increases, and a better, it actually provides a better metric path and better um, metric path, right? And now how this dynamic adjustment work, already we said that adjustments routes dynamically. So how it works, so here we can say that the first thing is router will detect the change, then it will send the updates to the neighbor, the neighbor updates the routing table, neighbors update the routing table, and then after the network covers to a new optimal path. Okay, so here in this example we can say that in OSPF, when a link failed, routers run shortest path OSPF algorithm again to find the new shortest path. So do not worry about all these protocol terms. Okay, because we are going to learn or we are going to discuss that concept in this session only. Okay, so here shortest path algorithm or OSPF algorithm, what are they, that we are going to learn. Okay, so do not worry, whatever the concept we are discussing now, just go through it. Okay, now fourth point we can say that more efficient in large dynamic network. So here adaptive routing is best suited for adaptive routing is best suited for internet enterprise network, ISP network, and large WANs. So here as we said, it is more efficient in large dynamic network. So we can say that it actually give importance to automatically adjust to the failures. Okay, why it is efficient, or why it is efficient for the large, or why it is known as the dynamic network. So the answer, we can say that it is actually giving importance to automatically or automatic adjust to the failures, balance network load, and it will avoid the congestion. It gives shortest or least cost path. Okay. Now, the static routing would fail or cause packet loss in such large environment. That is also a problem. That is also a problem, right? Like when it comes to dynamic, it is giving all the plus point. When it comes to static routing, it actually fails. Why? Because we can say that packet loss, it is not suitable. The first thing is, it is not suitable for the large environment. It is for the short it is for the small environments only. Okay. So as it is, its working nature at is as it is working in a static mode, it is suitable for the small environment. And the adaptive routing, it can be work in a large environment because of its dynamic or its automatic adaptive nature. Okay, now when it comes to the last point, that is a higher overhead, means it actually overhead in the sense processing plus update both are happening here. So why this overhead is high over here or in adaptive routing? We can say the router must process routing updates, right? And it must run algorithms, right? It must store detailed routing information, yes. It must send updates or control packets frequently, right? So these are the reasons we can say that the overhead is higher comparatively the non-adaptive routing or the static one. Okay. Here actually there is one mistake in this area. This is dynamic routing. Okay, this is dynamic routing. Okay. Okay, so adaptive routing, it is dynamic. Non-adaptive, it is static. So this is just a typing error. Here it is dynamic. Okay, everywhere it is dynamic. Now the next one is okay, so here we have completed two important topics. That is, one is routing algorithm, and the second one is what is network layer, or what is the design issues of network layer. So that two portions are over. Now the third one is optimality principle, which is again very important. As in network layer, we are talking about how to select the shortest path, or how efficiently we can transfer or move the packets from source to destination in a short time or in a fastest way, right? So here again, one important concept which helps for this thing is optimality principle. Okay, so here in computer network, the routing algorithm we have already discussed. The in routing algorithm, the optimality principle states that from J to K is also a path of optimal path. So here this principle is a foundation for many routing algorithms, like we can say distance vector routing or link state routing. Here when it comes to distance vector routing, we can say Bellman Ford, and when it comes to link state routing, Dijkstra algorithm is the best example for that. These algorithms work by breaking a shortest path into smaller optimal subpaths. Okay, so here again I'm reminding, when it comes to the optimality principle, that optimality principle states that any subpath of optimal path is itself optimal if a router J lies on optimal path from router I to router K, then the path for J to K is optimal. Okay, so here we are going to learn it in a detailed way. Okay, before that, what are the where this optimality principle applies, or what are the applications of this optimality principle? So here we can say that it is used for constructing sing tree. Okay, it is used to construct sing tree, or else we can say directed acyclic graph. okay, which shows the shortest path from multiple source to the single destination. So a sync tree means it is built using the optimality principle to show the shortest path from all router, that is source, to a single destination, that is sync. It will ensure the loop free and efficient routing. So here sync tree help in efficient packet routing without loops. Also it routing decisions. It will reduce this optimality principle, okay, it will reduce the delay and it will improve the quality of service, and also it will provide the foundation for advanced and adaptive routing techniques, okay. So here the major thing that you have to remember, where what are the applications. The first application is decisions. It will reduce distance and improve quality of service. It will provide the foundation for advanced and adaptive routing techniques, okay. So here first is actually showing the image of, or it is a figure of network. It is a figure of a network, and the second one is a sync tree for router B, okay, sync tree for router B, which shows there is no loop, okay. Here you can see everywhere it is connected or there is a loop, but here you can see the end of the nodes, okay. Now the next important topic on this portion is flooding. So flooding is very simple non-adaptive routing broadcast technique. When a router receives a packet, it will forward the packet on every outgoing link except one it arrived on, okay. So here no routing table or topology knowledge is required. Now here we can say there are three major types of floodings, which is very important. First one is uncontrolled flooding, second is controlled flooding, and the third one is selective flooding. So uncontrolled flooding means each router unconditionally transmit incoming data packets to all its neighbor. This can lead to broadcast storm due to indefinite recirculation of packets, right. Controlled means use method like sequence number controlled flooding and reverse path forwarding to control packet transmission, and also it will avoid the infinite loops. Third one is selective flooding, means routers send packets only along paths heading approximately in the right direction, reducing unnecessary transmissions, okay. So again, if we summarize this portion, we can say that flooding is a data forwarding method where a packet is sent to all node in the network instead of choosing a specific route, okay, or instead of choosing a specific route. It ensures that if the destination exists, the packet will eventually reach it, okay. So here how this flooding work. So the first one is it will send the data, it will broadcast the data, it reception by all the device, whatever the connected devices are there, everywhere it will be received. It will inspect each device, check the destination address in the packet header. Then after it will filter. If the address matches, the device accept the packet. Otherwise, it will discard the packet. Then after it will propagate, or else we can say the device forward the packet to their connected neighbor. This repeat until the packet reach the correct destination. And finally, loop prevention means to avoid infinite circulation of packet. The techniques like time to leave or sequence numbers are used, okay. So here these are the way, okay, or else we can say these are the important 7 steps that the flooding happens or flooding works. How we can say that after all, whatever the information we are sending, whatever the data we are sending from source, it should reach to the destination, right. So what this flooding gives importance to that. It will forward this package to all the nodes which are connected to the network, okay. And once the network or once the node receives this information, or once the device, any device is receiving the packet, it will match whether the information is from this particular area and it is for me or not. If no, it will propagate, it will pass this information to the neighboring device. Okay, and finally it repeat until it reach to the destination. Okay, so this is the way the flooding work. Okay, so here, after all, actually we come to know that the major task of flooding is that information whatever we are sending, it should reach to the destination, right? So why do we use this complicated way of sending packet to the receiver? Why we are using this? So the answer is, we can say flooding is not used for regular communication. It is actually helpful for special cases, like we can say address resolutions. Okay, so here what happened, a device that knows the IP address but not the MAC address broadcast an IARP request. So here all the device receive it and correct device reply with its MAC. So this is the first one. Okay, the IP address is known but the MAC address is unknown. So what happened, when the device is sending any information, it will identify accordingly, like IP address and MAC address, accordingly it will be received by the receiver. Now when it comes to routing protocol, we can say link state protocol is an example for this area. So here router flood link state advertisement. So every router has the same view of network topology. Okay. Then after network discovery and announcements, we can say that similar broadcasts are used for printer or service discovery in LANs also. Multicast tree setup means some multicast routing algorithm use initial flooding to identify members of multicast group before building a distribution tree. And the last one we can say emergency broadcast means in critical cases like alarms or disaster recovery messages, flooding ensures that the message reaches every devices regardless of the location. Okay, so here what are the features of flooding? Already we come to know that these are the reasons that flooding we are using. We are not using flooding for regular communication, we are using flooding for special cases only. Okay, so here what are the features? The first feature we said, the broadcasting means send packet to all device, not just one. That is the meaning of broadcast, right? We are not sending only to one device, it is actually broadcasting the message. No prior knowledge is needed, work without routing table or topology knowledge. Okay, it is not working on the basis of a routing table or any knowledge about the topology. It is actually working without any prior knowledge. It is simple and robust, means it is easy to implement, there is no complex routing logics. Then after, loop prevention is also there. It uses mechanisms like time to leave or sequence number to avoid endless circulations. Okay, it will leave or it will live till the time or till the sequence. Okay, then used in a special situations like already we have discussed. Then after, security concerns means may expose data to unintended recipients. And resource utilization, all devices must process or discard the package. Okay, packets. So these are the different features of flooding. Now what are the limitations? Whatever the things we learn, whatever the things we learn in flooding, somehow some points we feel that it should not happen, right? Like the first thing which comes to our mind is that too many packets cause delay and reduce the performance, which leads to network congestion, right? The second thing is wasted bandwidth, as all the device get the packet, even if only one needed it, it is circulating or it is sending to everyone, it is broadcasting to everyone. So that is the reason that it actually cause bandwidth wastage. Sensitive data may reach unauthorized device also. Security risk, that is a very big security risk that sensitive data may reach to unauthorized device. Then after, device must process unnecessary packets using CPU or memory. So the resource consumption, that problem is also happening here. Unnecessarily the resources are consuming, right? Unnecessary resource consumption is happening. Now, in large network, traffic grows unmanageably. Okay, so the poor scalability is also a problem. Sending to just one device became wasteful, okay, because inefficient for unicast. It is giving importance to multicast, it is not giving importance to unicast. Then cannot prioritize traffic or control routing path, so limited control is there. Excessive broadcast can overwhelm a network, right? Then after, device may be offline or unreachable, so there is no guarantee that the packet which we have sent, it will receive, it will reach by the destination, right? It will handle loops and duplications become difficult, as it is actually difficult to in large network. It is difficult or it is complex in large network. So these are the limitations of flooding. So here, flooding, what do you mean by flooding? What are the types of flooding? How flooding works? Why do we use flooding? What are the features of flooding and limitations of flooding, which is very important you to remember all the points. Now we are going with a new topic, or the topic which we were discussing about I to J, J to K, like that, right? Optimality principle. So in detail we are going to know what it means. Okay, so you can see here one figure which was having all the different sessions, A, B, C, D, E, F, total six different uh, images you can see, or six images with different values you can see. Okay, so the first thing is, we are going to learn about shortest path algorithm. We are going to learn about shortest path algorithm. Okay, so here, the first thing, when you are learning about shortest path algorithm, first thing, prepare a table. Okay, prepare a table which was having all the node information. Second column should have the shortest distance, and the third third column should have the previous node information, so that it will be very easy as to calculate the shortest path. Okay, to understand the shortest path. Okay, so here, shortest path algorithm, we can say it finds the most efficient routes, okay, between two node in network by minimizing a specific metrics such as distance, delay, or cost. These algorithms use graph theory, where each nodes are devices and edges are links between them. So often with weights represents the metrics. So here, the most common type of algorithm, or the most common type which we are using for shortest path is Dijkstra algorithm, which finds the path with the lowest total weight from single source node to all other node in the network. Again, I'm repeating, you can pronounce it as Dijkstra algorithm or Dijkstra algorithm, both are same only. Okay, so how it works? So again, I'm telling the first thing is graph representation will be there. You can see the graph representation. Okay. Then each edge have weightage. Okay. You can see each edge have some weightage over here, right? And now how it work, right? So we are moving with that. So here the first thing, again I'm reminding you, node information should be there should be one table which should have information about the nodes. Second is about the shortest path, and the third is about the shortest distance, and the third is about the previous node. So initially when we start we are assuming that we are going to start from A. This is my starting node. Okay, so when I'm starting, the initial value we considered it as 0 only. And when we are moving b a b c d e f g h till these nodes, we were not knowing the actual distance from a to b, a to c, like that, right? So what we are doing at initial stage, we are putting a as 0 and the remaining all the values as infinity. Okay, so this is point number 1. Now when it comes to the second level, so we are started with 2. We have started with a, right? So a, we should check which one is the nearest nodes. Okay, which are the nearest nodes? So here a to b, then after a to g, two nodes are connected to a. So we are going with a to b. A to b, you can see that the um, distance from a to b is 2. Distance from a to b is 2. So what we did, we actually removed infinity and we change it to 2. Now the second node which is connected with a is a to g. So here you can see it is 6. Okay, if I want to reach from a to g, the distance is 6. So I cut down the infinity from here and I again put 6 here. Okay, and here if I want to reach a to b, a to b, okay, so here we can say that distance is 2 and b's previous node is what, a. And here also, if I want to reach to a to g, the distance is 6. The distance is 6 and the previous node of g is what, a. So what we did, we have added previous node as a and a here, and we change infinity to 2 and 6. Now the next point is, okay, as we are doing what we are doing, we are doing here shortest path, finding the shortest path. So here now I am going with B. I'm going with the node B because it was having the shortest value. So I considered it as that only. Okay. So here now B. What are the immediate connected nodes? So I saw that when it comes to B, the immediate nodes are B to E and B to C. B to E and B to C. Right. So here when it comes to B to E, B to E. So the value of B, now the value of B is what? 2. And the distance that B to E is what? It is also 2. So 2 plus 2, we can say 4. Okay. And to reach to E, what I did, I actually calculated the distance between B to E. So here the previous node is B. The previous node is B. Okay. The previous node is what? B. And the value is 4. Now the next one is the immediate node is again C. For B, the C one is the immediate node. So what I did, B to C, the calculation, the value, the distance is what? 7. And the value of B is what? 2. So 2 plus 7, it is 9, right? And what I did, actually I reach C from B. So the previous node is here B. Okay. Now, so what we did, if I wanted to reach B, the previous node is what? A. If I want to reach C, the previous node I identified as B. If I want to reach E, I identified B as a previous node here. And if I want to reach G, the previous node I identified as A. Okay, now if I consider the overall table, I come to know that the to reach b there is no other node. Okay, no other node which gives in a shortest way, okay, or shortest path. So I actually freeze that point. 2 is the shortest one, so I freeze that one. To reach a to b, 2 is the shortest distance, so I freezed it. Okay, now the next one is E. I'm going with E. Okay, I completed the visited nodes are A here. A I visited, B I visited, G also I have visited, E also I have visited. Now, okay, G I haven't visited. Actually, I reached to G, right? So A, B and E I have visited. So E, now I'm in E. So E, what are the connected network or connected node? So E, we can see F is there, E, G is there. So here we can see that when it comes to E to G, the value of E is 4, and to reach E to G, it takes 1, right? 1 value, 1 cost. So we can say that 4 plus 1, it is 5. Okay, so here initially it was 6, and if I consider that A as my previous node, okay, so it takes 6 as the distance. But when I am actually going from E, I'm actually reaching very fast, okay, because 4 plus 1 is 5. So what I did, 6 also was cutted down, and I put at 5 here, and my previous node to reach in fastest way is E. Okay, to reach to G, the fastest node is what? E. So I wrote here E. Now, what is the next immediate node for me? That is F. So let me see. E to F, it is 2, right? 2. E to F, it is 2. And the value of E is what? 4. So 4 plus 2, that is 6. That is 6. So here also what I did, I wrote here 6. And here the previous node is what? E. Okay, so till this portion means I actually visited A, B and E. A, B and E. These much portions I have covered. I reach after once I covered A, B, E, I actually reached to G. I also reached to F, right? Now I am actually moving to the next node, that is I'm going with G. I'm going with G here. Okay. So if I consider G, okay, okay, listen. The arrow which shows here, no, it indicates the next node. It indicates the next node which we have to focus. So here, okay, if I go with F, chalo. So the first thing is F. The value of F is what? 6. The value of F is what? 6. Now, immediate node which I am getting from F is C and H. So if I want to go to F to C, what is the total cost? What is the total cost? We can say that 6 plus 3, right? 6 plus 3. So that is 9. 6 plus 3, that is 9. So I am writing here, suppose 9. Okay, if I am writing here, sorry, if I am writing here C as 9, okay, no need to change because it is already 9 only, right? So the first one is B to C distance was also 9, so no need to change because it is similar. 6 plus 3 or 7 plus 2, both are similar, so no need to change. So I'm not changing here. The previous node is B only. To H, F, the value is 6, and reach to H, I am having 2 as a value. So 6 plus 2 is 8. Okay, so here the previous node is F and the value I changed to 8. Okay, and now we can see that which is not visited link here. So I'm going with G. So here G to H is the immediate, G to E is immediate. So here already we have covered that, right? So no need to move on that stage. But G to H, so G to H, the value of G is 5, and reaching to H, it is 4 is the distance. So we can say 5 plus 4, that is 9. So when it comes to G to H, okay, the value of G to H, we can say here, okay, sorry, because G to H is 9 and F to H was the shortest path, right? F to H was the shortest path, which is giving 8 as a value. So we considered that, okay, F to G. So here the previous node is F because it was the shortest one. As it is giving the longest path, we are not considering that. Again, I am telling you, please remember, we are finding here the shortest distance, shortest path. So here it is already verified that it is giving the shortest way. So we are the largest value. Okay. Now the final one is H. If I am into H, this is my next node. H to the next node or the neighboring node, we can say F is also there, D is also there. So F is already covered, so we are going to D, or F is already visited node, right? So now we are going to D. So H to D. So the value of H is 8 and the value of D is 2. So 8 plus 2, right? H to D. The value of H is here, it is 8. And if I am reaching to D, if I want to reach D, the distance is 2. So here we can say 8 plus 2. 8 plus 2, 10. So what happened? Here in D, I cut down the infinity. Here also it should cut down. Okay. It should cut down the infinity. And I am putting 10 and the previous node as H. So here the thing is, suppose this is my initial node and this is the last node. If I want to reach from A to D, the shortest path I am getting is 10. Shortest path or shortest distance I am getting is 10. How? We will check. Okay, we are into this node D. D, the previous node is what? H. D, the previous node is what? H. We will check. I am in this position D. D to previous node H. So here it is 2, right? Now H, I am in H. Okay, here H, and now what is the previous? It is F. Okay, again 2. Now F. Okay, F, what is the previous? E. Okay, so E to F to E, it is again 2. Now let me check E. E, what is the previous? B. Okay, I reached to B. Now for B, what is the previous? A. So I reached A. So if you calculate 2 plus 2, 4 plus 2, 6 plus 2, 8 plus 2, 10. Okay, so in this way also we can recalculate or we can verify that whether the path which we receive or which we have identified is right or not. Okay, so here this is also cut down. Okay, this is also the cut down portion. Fine, this infinity is not there in this. All this infinity portion or this all infinity value we put when it is in an initial stage. Okay, so again I am repeating, we may be getting question as this one. We are going to get the question like this one. This is my graph, and it will the question will be like, with this graph identify the shortest path, from node A to node D, or else identify the shortest path. That's it. Okay, so if this kind of graph is there, what you will do, first of all you will make all the 3 columns. You will write the node, you will write the shortest distance, you will write the previous node, and then once the nodes are written, the initial value will be always 0, and remaining the distance we were not knowing. So what we are doing, we are putting it as infinity. And now the previous node, it comes from the initial to the next nodes. Okay, so initial A, the next neighboring was B and G. So accordingly we have calculated the things. Okay, so go through the portions again properly. Here again I'm reminding this is a printing mistake, so here you have to cut down. This is also cut down portion. So the final is 0 2 9 10 4 6 5 8, and here it is A B H B E E F. This is the previous node. Okay, fine. So now the next one, the next important one is distance vector routing. Again, by using distance vector routing also, we are determining the shortest path of data to travel between the routers. Okay, so distance vector routing is a protocol used in a computer network to determine the shortest path for data to travel between the router. Each router maintains a routing table that contains the distance or the cost or to each or to every other router in the network. This distance is typically measured in the term of numbers of hops or the steps required to reach the destination. The protocol relies on routers periodically sharing their routing table with their immediate neighbor to update and optimize the path. Okay, so like in shortest path algorithm, by using an example, we try to understand the concept. Same way, by using some example only, the concept of distance vector routing in detail. Okay, so here again I am repeating, the distance vector routing protocol is based on Bellman-Ford algorithm, and the shortest path was about the Dijkstra or Dijkstra algorithm, right? So it is about Bellman-Ford algorithm, which calculate the shortest path by iteratively updating the routing table. Okay, each router evaluates the cost to its neighbor and combine these with the neighbor's routing information to compute the best path. So here the main features which is included in distance vector routing are periodic updates, knowledge sharing, and dynamic adjustments. Okay, so periodic updates means routers share their routing table with neighboring neighbors at regular interval. Second is each router will communicate its view of network to its neighbors, allowing them to update their own routing table. And the third one is when a topology change or occurs, any kind of failures, router recalculate the path and propagate its updates. Okay, so here in this example you can see the four routers A, B, C and D. The weights are also mentioned at the edge. A to D is 1, right? D to C is 11, C to E is 3, B to A or A to B is 2, B to D is 7. Like that, all the edges having its weightage. Weightage could be the distance or cost of delay. Okay, so here the starting one, um, when there is a question about distance vector routing, again you will get an image like this, and accordingly they will ask you to calculate the shortest distance. Okay, so for that, the first step is each router prepares its own routing table. Okay, so we are preparing here its routing table. So the first routing table, it is having three columns: destination, distance, and next hop. The second one is again for the router B. So here the destination is A, B, C. Distance is 0 to infinity 1. Okay, 0 as it starts from A. It starts from A. So we are considering it as a 0. Okay, then when it comes to B, it starts from B, right? When it starts from C, the distance will be 0 again, and when it starts from router D, the initial value or the initial distance will be 0. So accordingly it was calculated. Okay, okay, this is again about the next hop, and this is about the destination, this is about the distance. This way we router exchange its distance vector obtained in step 1 with its neighbor. Okay, how it is actually exchanging the distance vector. Okay, so here this is from B and this is from D. Okay, 2037, 2037, right? This is the distance 2037, and I am taking value from D. So here also the D value is 17111, 17110. Okay, so this is the value. So here now we are going to create a new routing table which is giving, let us see that is it giving a shortest path or not. Okay, so how we are going to calculate the cost of reaching destination B to A, B to A. Okay, B to A. So here this is the starting, right? So what we are doing, uh, B to A, sorry, B to A. So here what we are doing, the cost of reaching A to B is 2 and cost of reaching A to D is 1. So accordingly we are calculating. Okay, so 2 plus 0, 2 plus 0, 2 plus 0, and 1 plus 7, 1 plus 7. Okay, here already the first hope is given, so we are calculating from this area. First one is given, so the remaining we are calculating. So here cost of reaching destination B from router A, destination B from router A, that is 2 plus 0 and 1 plus 7. So 2 will be the answer, right? 2 plus 0 is 2, 1 plus 7 is 8. So 1 plus 7 is actually higher value. So we are not considering 1 plus 7 is 8. So we are not considering. So we are calculating 2. We are calculating 2. Okay, and the hope is B. Now again 2 plus 3. 2 plus 3. The value is the A to B is 2, right? A to B, the distance is 2. So 2 plus 3, that is 5. Here it is about 1. So A plus D, right? A to D, it is 1. But it is 11 plus 1 or 1 plus 11. So again it is about what? 12. So we are not considering it as a shortest path. So we are going with 2 plus 3, which is 5. So we updated here as 5. Now the third one is 7 and 0. So 7 plus 2 is 9 and 0 plus 1 is 1. So we are going through D. We are going to through D, means 1 is the shortest. So we update here 1. So the new routing table at router A is this one. So now this is the router table of A. Okay, this is the router table of A. Now we'll go with router B. So here for router B, okay, we are having 3 nodes A, C, D that we can reach to B, okay, or we are having the connectivity from B. We are having the connectivity to A, C, and D. So we are taking all the neighboring nodes, okay, or neighboring routers. So here the values of A are 0 to infinity 1. Let us see 0. Okay, here the distance is 0 to infinity 1. Okay, then after here C is infinity 3, 0, 11. D is 1, 7, 11, 0. So we are updating the same information over here also. Okay, so now the shortest or the path, the cost which is used for reaching B to A is 2, B to C is 3, and B to D is 7. From where we are getting all this? We can say that it is available from the first graph. It is available from this graph. A to B is 2, B to C is 3, B to D is 7, D to C we can say 11, A to D is 1, right? Okay, so this is the way we are getting the information. Okay, so here router B, so B to A is 2, B to C is 3, and B to D is 7. So now we are calculating. So we are in B. We are in the B router, so this area we are not doing anything. So the first one is here A from router B, A from router B. So here 2, okay, plus 0, 2 plus 0, then 3 plus infinity, then after 7 plus 1. So which one is the smallest? We can say the 2 is the smallest. So we are updating here 2 and the hope is A. Okay, via A I got it, the shortest path, right? Now the next one is this is the freeze area. We are not going to do anything because from here we have started, right? Now the C part. Okay, so for that 2 plus infinity, 3 plus 0, and 7 plus 11. 7 plus 11. So which one is the shortest? 3 plus 0 is the shortest. So we have updated here 3. Now the next one is 1, 11, 0. So we will check 2 plus 1, 3 plus 11, 7 plus 0. So which one is giving the shortest? 2 plus 1, which is 3, via A we are getting. So here we have updated A, and this is the shortest path. This is the shortest path for router B. Moving to C, the same way. C to B is 3, C to D is 11. Accordingly, when it was calculated, 3 plus 2 and 11 plus 1. Which one is the shortest? We have identified 5 as shortest. So 5 was identified here and 5 was written here. Second is 3 plus 0, 11 plus 7. So which one is the lowest? We can say this one, 3 plus 0, 3. So we have added 3 via B is the easiest way. Thereafter, this is the freeze area. From here we are started. Okay, so we are not going to this area. Now the 7 plus 0, 7 and 0. So here 3 plus 7 and 11 plus 0. 3 plus 7 is 10. So it is again the smallest one. So we have added 10 here. Now when it comes to router D, so this is the, from this point we are going to start. So here again D to A is 1, D to B is 7, and D to C is 11. So according, so here 1, 0, 7, 2, 11, infinity. It is very easy to identify that yes, 1 to 0 is the shortest. So we have added 1 and the next hope, or from A we reach here. Then after 1, 2, 7, 0, 11, 3. Again it is very easy to understand that 2 is this one is the shortest. So here we have added 3. 2 plus 1, 3. Now the next is 1 plus infinity, 7 plus 3, and 11 plus 0. So here 1 plus infinity is very big value, right? We cannot identify what is the value. 7 plus 3 is 10. 11 plus 0 is 11. So here also 7 plus 3, 10 is the shortest. So we have added 10. Okay, so this is the new routing table for D. Okay. Now in the next step, each router exchanges its distance vector obtained in step 2 with its neighboring router. After exchanging the routing vector, each router prepares a new routing table. So now this time we got the new routing table. Okay, and again we are actually checking whether the information which we reach, that is the shortest one or not. So again we are calculating the value. Again here B and D, so A to B is 2 and A to D is 1 here. So accordingly we are calculating. Here we reach the, we got the new one, that is, this is the starting. So here from B, B, D we got initially, what was the answer? Initially the answer was B, B, D 251. 251 was the answer. And this time we are getting, this time 251. Okay, so this is the shortest one. No need to change anything, right? Thereafter getting here BCA and the values are 033. 2033, and this is the updated value which we are checking here, the updated routing table. From that we are checking the information. So here previously router B we were getting the information as 2033. So in this time when we calculated the same, so again we need not have to change anything, it is the right one. Then after 5306 in this, it is about C. Okay, 53010, it was 53010. Okay, in C previously it was 53010. So by using the new distance value, when we have calculated, we got the router, the easiest or the nearest path as 5306. Okay, then again 1360 for router D. So initially it was about 1310 was there, 1310. So it is again changed. When it comes to D, it was 1360. So this is the shortest one. Okay, so here finally we have identified the router distance, the shortest router distance over here. So here identify the why we are okay. So finally by using these steps, okay, by using these steps we come to know, we prepare the routing table and accordingly we calculated the distance between each routers, right? And finally we got the shortest distance for each router to travel, each routers to travel from its source to destination. Okay, now here what is the again what this distance vector router doing, or what it does, right? So we can say that it identifies the unused links. Okay, that is the first purpose that router vector uh, distance vector routing doing. Okay, so here the identify the unused links after routing table. Okay, when it became stable, some of the link connecting the router may not be used. Okay, so like we see in the above example, and we have already identified. So here we can say we have the value of next hope in the final routing table of router A suggested that only the edge A, B and AD are used. So remaining all the nodes are unused. Then after in the next hope in B, we come to know that BA and BC are used, not the remaining. When it comes to the hope of 6 C, we come to know that CB is used, not the remaining used. And the last one, when it comes to D, DA was used and not the remaining routers. So thus the edge BD and CD are never used from this router table. When we prepare this router table, we come to know that BD and CD are never used. Okay, so by using distance vector routing, we can identify the unused links also. Okay, so the points to be remember on this point is only distance vectors are exchanged, not the next hopes. Okay, this is because it result in exchanging the large amount of data which consumes more bandwidth. While preparing a new routing table, a router takes into consideration only the distance vector it has obtained from its neighboring router. It does not take into consideration its older routing table. This algorithm is called so because it involves exchanging of distance vector between the router. Distance vector is nothing but an array of distance. The algorithm keeps on repeating periodically and never stops. This is to update the shortest path in case any links goes down or topology change. Routing tables are prepared total n minus 1 time if there are n routers in the given network. This is because the shortest path between any two nodes consists at most n minus 1 edge if there are n node in the graph. Okay, and distance vector routing suffers from count to infinity problem, and distance vector routing uses UDP at transport layer. Okay, so remember all this point, it is very important. You can expect the Dijkstrap algorithm, Dijkstrap algorithm, or this distance vector algorithm in your paper. Okay, any of one or both you can expect. This is very important, two questions. Okay, now the next is link state routing. So link state routing, we can say it is a dynamic routing protocol in which each router depends, okay, each router independently built a map of entire network and communicate the shortest path to each distance using algorithm like Dijkstrap. Okay, so in contrast to the distance vector routing, link state routing is typically to converge and more reliable in large network. Three separate tables are created on each link state routing enable router. One table is used to hold the details about the directly connected neighbors. Second will hold the topology of the entire internetworking, and the last one will hold the actual routing table. Okay, and the examples of this link state routing protocols are open shortest path first and intermediate system to intermediate system, is. Okay, so these are also routing protocol that are considered to be hybrid in sense that they use aspects of both distance vector and link state protocol. Enhanced interior gateway routing protocol is one of those hybrid routing protocol. So here how it works, or what is the way, how what informations it what are the important informations that it gives importance. Okay, so here the first one is link state routing. We can say it will discover how it works. Okay, how it works, we are talking about that only. So the first one is it will discover its neighbors and build its neighbor table. Okay, so for that, to prepare the neighbor table, so for that what it is doing, each router periodically send a hello packet on each of its link to discover directly connected neighbors and establish the connection. Routers use response to build a table of neighboring router. Now, second point is measures the link cost to each of its neighbor. Third one is building and distributing link state packets. Each router constructs its link state packets which contains its identity, a list of its neighbors, and the cost of each neighbors. Okay, then after, link state protocols are sent throughout the entire network. So each router receive information about each other router's neighbors. And here sequence, numbering, and time to leave or time to live field in link state protocol prevents loops and steal the informations. Okay, and the fourth one is building the network topology database. That is the fourth step. Here, once a router has received the link state protocol from all the routers, it construct a complete map of the network. This map allow each router to see the full network and not just adjacent connectors. Fifth one is calculation with Dijkstrap algorithm, and the last stage is reacting to the network change. So here all routers use link state routing, thus maintain up any updates, synchronize the view of network, and react quickly to the changes, make it highly reliable and scalable for the modern network. Okay, now moving to the next topic, which is admission control. Okay, so admission control is a network mechanism, okay, which is used to decide whether to accept or reject the network traffic flow based on the available resources. Okay, it ensures that the network is not overloaded by limiting the number of active connection, helping maintain quality of service by preventing congestion before it occurs. When a flow requests the admission, the system check if the resource are sufficient. If not, the flow is denied admission. Okay, so why this admission control is needed? So we can say to avoid the congestion collapse, preserves the quality of service. Okay, it will preserve the quality of service, or it will guarantee it, and efficient multiplexing is also the plus point, or that is the reason that we are using admission control in networking. Okay, so here you can see one example of admission control. Okay, this is a mesh type of network, you can see, right? Mesh type of network connectivity, which is actually due to some congestion, the packet loss is happening, or there's some network congestion is happening there, so that the communication is not possible. But here you can see the virtual circuit, because of that there is no congestion happening on this portion. Okay, so here the what are the types? We can say the call level admission control and packet level control. These are the two different types of admission controls. It operates at the connection level, admit or reject calls, resources based on aggregate availability. Means this check whether an entire connection can be accepted or not before it start. Packet level admission, it focuses on quality of service profile of the packets like arrival rate, delay, loss of request, etc. Okay, for more granular control, each packet is checked individually to see if it fit the network capacity or quality of service rule. Okay, so you can see both the differences. Here it is a mesh type network. Okay, which is interconnected, or mesh type means it is interconnected only. Okay, because of that some net congestion is happening, and here it is having a virtual circuit. Because of that there is no chance of congestion. Now, okay, so here remember the points, it's very important. Admission control is also an important topic that you can expect for minimum 3 marker. Okay, or you can expect for 1 mark also, as it is a important point when it comes to the networking. Okay, next one is load shedding. It is very important one topic which you can expect for 7 marker also. Okay, or else minimum please expect for 3 marks. It is very important topic, please go through it. So here load shedding is a congestion control technique used in computer network to provide the system when the traffic load become too high. Instead of letting the entire network slow or crash due to excessive congestion, the network intentionally drops some packet or refuse new traffic. Okay, by sacrificing less important data, the network keep essential service running smoothly. Okay, so here load shedding is a congestion control technique. Why we are using in this in computer network? To protect the system. Okay, to protect the system when the traffic load became very high. So when the traffic load is very high, we can say that the entire network can down. Okay, the entire network can slow down, or there are chances of crash because of excessive congestion. So rather than that area, or it will actually, it prevents to go with that problems, it will prevent from that area. How? By sacrificing the less important data, it will actually sacrifice, or it will discard the less important data, and it will work with essential services. Okay, it will run with essential services. So here, why, again the question is why it is needed. So the answer is very clear, why it is needed, right? Because it is giving importance to the less important data, and try to keep the network or it will prevent from network congestion. It will prevent from network congestion, or it will prevent from entire network to slow down or to crash the entire network. So that is the reason that load shedding is that technique is used. Okay, now, so the first thing is, when the router became overloaded, their queue start filling up. Okay, if the queue became full, router may stop dropping all incoming packet. These can lead to the network collapse where no service works properly. To avoid this, the network selectively throw away less important packets earlier. This is called load shedding. So load shedding work on the principle better to lose some packets than lose the entire network. Okay, so the meaning is instead of allowing congestion to grow uncontrollably, the router control the load by discarding certain traffic so the remaining traffic gets enough bandwidth to flow smoothly. Okay, so I hope the load shedding, the concept is very clear for everyone that load shedding is a congestion control technique. It is a congestion control technique used in computer network to protect the system, from what, to entirely slow down the network or the network crash. Okay, how it is doing? It is actually discarding the less important data and giving importance to the essential service so that it can run smoothly, it can work smoothly. Okay, and the principle behind the load shedding working is better to lose some packet than lose the entire network. Okay, so here how this load shedding works, we can say already we have discussed here. Okay, why it is needed in that portion only, it was very clear how it works. So the first one is it will the router detect the congestion. Yes, because it the queue size is when the queue size increases. Okay, and so that what happened, the process delay will also increase and the buffer will overflow, the buffer will overflow, so the router will detect the congestion accordingly, right? Now, the second point is router identifies packet that can be dropped. So, what are the chances of that the packet can be dropped? The first one is we can say the lower priority packets can be dropped, non-critical data can be dropped, traffic from source sending too much data, that also can be dropped, and sometimes the random packets also can be dropped from this load shedding technique. Okay. Now, the third point is router drops or shed the selected packets. Okay, so what is happening, freeze the buffer space, it will reduce the load and also it will prevent the collapse of forwarding the queue. Okay, when it comes to the fourth point, we can say high priority traffic continues smoothly, means it is essential service, essential services are preserved, essential services are preserved, and overall network stability also will improve because of this high priority traffic. Okay, because of this high priority traffic. Okay, so here again the first point was because actually we are giving importance to the router detection technique. Okay, what happened, how it is doing, when the queue size increases, the process delay also will increase and the buffer is about to overflow. These condition will be detected by the router. When it will be detected, what it does, it will identify the packet that can be dropped and what kind of packet it is going to drop, which was having low priority, which is not a critical data, which doesn't have any critical data, traffic from the source sending too much data, and sometimes the random packets also can be discarded or dropped. Okay, now what happened when the router drop the selected packets or sheds the packet, it will free the buffer space, it will reduce the load and also it's of forwarding queue. Okay, now these all part is happening or all the things are working smoothly, we can say that it is giving importance to high priority traffic. Okay, so how we can say that essential services, when we are giving importance, we can say that essential services, when we are giving importance to the high priority traffic, we can say that it will preserve the essential information priority traffic, we can say that it will preserve the essential informations or we can say that it will preserve the essential informations or essential services, and it will improve the overall network stability also. Now, what are the, again, there are two types of load shedding. We can say priority based load shedding and the sorry, there are three types of load shedding: priority based load shedding, random packet dropping, and flow based shedding. Okay. So here packets are dropped based on the priority level. So that is priority base. Okay, high priority, low priority, and medium. So the high priority means voice, video conferences. We cannot drop anything from that area. Medium means web browsing. We can skip some information while browsing the information. Bulk download, there obviously it is giving low priority. Okay, so the low priority will be discarded first. Now the random packet dropping, when the priority information is not available. Okay, router drop packets randomly. Okay, random early detection will happen. So the third one is flow based shedding. Entire flow that overload the network may be dropped, used when some user or application send very high traffic. Okay, so these are the three different types of load shedding. And now what are the advantages? Prevent complete congestion collapse. It will keep essential service running. It will improve the fairness by controlling the aggressive flow. It will give the quick reaction, means it will stabilize the network immediately. It, and also it is simple to implement. So here the takeaway from this part is, load shedding is a fancy way of saying that when router are being inundated by packets that they cannot handle, they just throw away. Okay, now some small topics we are going to discuss now. In between there may be some 7 marker will come. So here the first thing is random early detection. It is proactive congestion avoidance algorithm used in router. It will monitor the average queue length and starts dropping packet probabilistically before the queue is full. This early packet dropping signals the sender to reduce its transmission rate, prevent the congestion built up. Okay, and this random early detection avoid global synchronization, means where many connections reduce sending rates simultaneously. Okay, and it operates by calculating the average queue size and adjust packet drop probability accordingly. Okay, so here random early detection, it is actually about what we can say is a proactive congestion avoid algorithm used in router. Okay, and it will monitor what the average queue length and start dropping the packets. Okay, packets before buffer became completely full. And it works by calculating an average queue length and drop the packets with increasing probability as the average length grows, sending an early signal to protocol like TCP to slower down their transmission rate. This is more efficient than traditional tail drop method, which wait until the queue is full to start dropping the packet. Okay, so here the benefits: avoid the congestion, it will avoid global synchronization, and also it gives proper fairness. Okay, now the next one is explicit congestion notification. So this is also a network mechanism where routers mark packets instead of dropping them to signal impeding impending congestion. When an ECN or explicit congestion notification capable sending receiver this notification, it reduces its transmission rate. Okay, and this is useful because it avoids unnecessary packet loss while still providing congestion feedback to the source. Okay, so again, if we detailedly talk about explicit congestion notification, we can say this allow the router this allows the router to signal impending network congestion to endpoint by marking the packet. Okay, by marking the packet, this is the way it mark the packet. Okay, mark the packet instead of drop them. This allow the sending device to proactively reduce its transmission rate before packets are lost, which will improve the efficiency and reduce the delay. So here, if we talk about an example, a router marking a packet's ECN bit, the destination echoing the congestion experience flag back to the sender, and the sender then slow down the data rate. Okay, so here we can say that in this image you can see the congestion signal. Okay, here the packet which we are sending, one by one the packet we are sending. Here what happened, here the multiple packets, it receives the multiple packet. So so here the congestion happened in this router. So what happened, it will mark the congested, it will mark the congested information, okay, or the congested packet, and accordingly it will transmit the information. Okay, so here it will flag back to the sender, and the sender then slow down its data rate, right? Okay, so please, again I'm repeating, please go through the session. If it is not clear, read it again or listen it again, it will be very clear for you. Okay, next one is chalk packets. Okay, chalk packets. So here chalk packets are the congestion control, which is very important topic from this session. Okay, chalk packets are congestion control mechanism used in computer network to tell the sender to slow down its transmission rate when the network is experiencing congestion. Okay, so in the last sessions we were learning about that only, right? We were learning if it is about admission control, if it is about load shedding, if it is about the early random early detection or explicit congestion notification. Everywhere we were talking about what the congestion control mechanism only, or the problems which occurs during the transmission, right? The congestion which experiencing in the network. So they act like a warning signal. When it comes to chalk packet, we can say they act like a warning signal sent back to the source to reduce the traffic and avoid the congestion collapse. So why this is needed, we can say when the router gets overloaded, their begins to fill. It reduce continuous it if traffic continues at the same speed, router may drop packets or it will crash. So to prevent this, okay, to prevent this, the router inform the source to reduce sending rate. This feedback is sent using a special control packet called chalk packet. Okay, so here when the router get overloaded, the queue begin to fill, right? So what is happening, if the traffic, it is already overheaded, if the traffic continue the same speed, so what happen, the packets which are there in the router may drop or it may crash. So to prevent that problem, what we are doing, the router will inform the source, it will inform the source that to reduce the sending rate. So this feedback is sent using a special control packet called chalk packet. Okay, so here you can say how this work. Again, already maybe you understood how it works, right? By seeing this image we will come to know more clearly. Okay, chalo. So here this is the way it move. We consider it as a network. Okay, so A, B, C, D, E, F, like this the network are connected. So A is sending some information to B to E. Sorry, A is transferring information to E to F to D. Now, here when it reached to D, it identify a chalk, it identify a problem, a congestion. It was sent, it was sent back. Okay, it was sent back. Once it reached to A. Once it reached to A, what it is doing, it will reduce the flow. Okay, it will reduce the flow, and flow is when once it reduce the flow, what happened, we can say that the flow from the source and source has been reduced, and the network is now, what we can say, it is less congested. It is less congested. The flow is still at a maximum rate only, right? It is in a less flow, or we can say it is going in a lower speed. Okay, so what happened, the chalk was identified and it was removed without any issue. But in the second stage, or in the second example, AEFD, okay, here the heavy flow was identified, heavy flow is happening, chalk was identified, or the congestion was identified. Okay, here chalk actually the from D to F, F to E, E to A, it is actually reaching to A. But before reaching to A, what happened, the it was completely, the entire network was completely gone down because of the congestion, because it was not reached at a time. The information, the congestion, the chalk packet was not received at a time. Because of that, what happened, the entire network was slow, we can say. Okay, so here a chalk packet is generated at the congested router and the travel back to the source. However, on its way, each router, the receiver receives the chalk packet, also reduces its on flow rate. Okay, it reduces its on flow rate. So what happened, the router along the path progressively reduce the flow rate even before the chalk packet reaches the source. So here, by the time the chalk packet reaches the source, all the affected router have reduced their transmission rate, leading to the network wide reduction in congestions. Okay, now moving to the next. Okay, so here again, this is very important part. Remember the points, it's very important. Next one is leaky bucket algorithm. As the name indicates, okay, we can say that if the information which is sent from source to destination is continuous, or the transmission speed is continuous, what happen, it will not reach to the destination, it will overflow. It will overflow. So the same concept is applied here. So the leaky bucket algorithm is a popular traffic shaping and congestion control technique in computer network. It regulates the rate at which data packets are injected into the network, smoothly out bursty transmission to a steady, predictable rate. So how it works, we can say that conceptual model means it will imagine a bucket with a small hole in the bucket. Incoming packets are poured in the bucket, means into the buffer. Water leaks out, okay, at a constant rate of R. It's not RR, it's R, constant rate of R. Related regardless of rate at which packet arrives. Now the bucket capacity, we can say it's B. It's not BB, it is again a printing error. Okay, so it's B. The bucket can hold only a limited amount of data. If the packet arrives at the bucket is full, the excessive packets are either queued or discarded. Okay, and the constant output rate, we can say, no matter the input patterns burstness, the leak rate set a strict cap on how quickly the packet can leave. This guarantees the network sees a predictable, smooth flow, reducing the chance of congestion. Okay, so we'll see the practical working. We will see the practical working of leaky bucket. Okay, again remember there are conceptual model, there are bucket capacity, and the constant output rate. Accordingly, it works, but still we will go with the practical working concept. So here what happened when a packet arrives, it will check there are enough room in the bucket. If so, it will add the packet. If no, it will drop the queue. It will drop the queue. The packet transmission, we can say the network interface transmit the packet from the bucket at the fixed rate, that is R, and then when the bucket is full, the incoming packet must wait or it will discarded. The algorithm convert bursty input traffic into steady stream entire the network. So here the leaky bucket help network avoid sudden congestion due to burst and support fair bandwidth allocation among user and applications. Okay, so you can understand, just see the image and try to understand what is happening here. Okay, so the first one is a network system which was actually sending the packets. Okay, so you can see that check bucket here. Okay, so what is happening with the other another example? So these are the packet which is actually we can say overflowing. Okay, which is overflowing or which is in a very high transmission form. Okay, so what is happening if the same happens here? If it is a leaking option, it will leak, right? Or else if it is the chance of availability, the buffer is free or the bucket is free, what is happening, the packets can be reached to the destination, or packet is there in the bucket, we can see, right? Okay, so this is about the token bucket. That is also the next topic which we are going to learn. And this is about the leaky bucket concept, that if it is available, it will be inside the buffer, it will be there in the buffer. No, then what happen, it will overflow, or we can consider that there is a hole in the bucket. So what happen, it will overflow the information, it will discard the information, or it will overflow the information, right? Okay, now the next one is token bucket algorithm. So the token bucket algorithm is widely used network traffic management method for traffic shaping and congestion control. It allow burst of data but enforce an average transmission rate, making it more flexible than leaky bucket approach. So again, how it works? So here bucket and token. So picture a bucket that can hold up to B token. Okay. So here you can see in the previous image B. Okay, this is the rate. Okay, this is the capacity. Now token are generated and added to the bucket at the fixed average rate, that is R. You can see here the fixed rate which is R. Okay, now packet transmission. To send a packet, the host or the router need to remove a number of token equal to the packet size. If enough tokens are available, the packet is sent immediately and correspondingly tokens are removed. If the tokens are insufficient, if there are if they are enough tokens, the packet is either queued until more token arrived or dropped. And here the last one we can say burstness, means token can accumulate while the host is idle, allowing for transmission burst as long as there are enough token in the bucket. Okay, so here one more working example we have added. Okay, so what problem does it solve? When it comes to token bucket algorithm, we can say it will prevent the device from overloading the network without too much traffic. Also, it will send data continuously at very high speed, but it still allow temporary burst when necessary. Okay. So here in the topmost row, you can see that it shows a data burst at 1000 Mbps for 125 milliseconds. Then the what happened, then the rate drops. Okay, then the rate drops. This is typical bursty transmission when which can overwhelm network buffer if sent irregularly, okay, or if it's sent unregularly. Now here you can see that the bucket is filled rapidly up to 16,000 kb, that is full burst size. The bucket hold the burst and drain as data is transmitted. Now in this portion you can see that the host now use the token bucket with the rate of R, that is 200 MB, that is 200 MB. Okay, Mbps, and the bucket capacity is 96 kb. The output rate is steady. The output rate is steady over here, and the burst is spread out over the time rather than sent all at once. Okay, and here the bucket is filled. The bucket is filled by the burst and drain. What is happening? It steadily. Eventually, the bucket empty. The transmission rate is delayed until more tokens accumulate. Ensures that the further burst cannot be sent until the bucket refill. In here, the bottom row, rate versus time, here we can say there is no buffer. Shows a token bucket with R rate as 200 Mbps or 25 Mbps. It's again a printing mistake. It's 25 Mbps. Okay, so 25 Mbps, but the bucket capacity B is equal to 0. The bucket capacity is equal to 0. The output rate is always 25 Mbps with no probability for bursty traffic or temporary storage. And here the bucket is always empty because it cannot hold any excessive packet. Traffic is instantly limited to the fixed rate. Okay, so here with this example you will come to know that how this token bucket algorithm works, okay, or what it is aiming to solve. So keep it in your mind that it prevents a device from overloading the network with too much traffic, and also it will send data continuously at very high speed also. Okay, so here this two concept, leaky bucket algorithm and token bucket algorithm, this portion is over. So again, if there is any doubt you can ask. Okay, so here if we compare, okay, if we compare both the statements, both the algorithms, leaky bucket and this token bucket, okay, any of this question you can expect in paper because it is very important one. So here if we come to discuss about the differences, or if we compare leaky bucket and token bucket, we can say that the first thing is, if I talk about leaky bucket algorithm, packets enter the bucket and leak out at the fixed or a constant rate, right? And that is the basic idea behind leaky bucket, right? And when it comes to token bucket, we can say tokens are generated at a fixed rate. A packet is sent only if the token is available. Okay. Then the second point that you have to remember when it comes to the control part, it will control the output rate. Okay. And here, when it comes to the token bucket, we can say the control the amount of data, means burst size plus its rate. Okay. When it comes to the leaky bucket concept, we can say that it does not allow any kind of burst. It will send the data at a fixed rate. But when it comes to token bucket, we can say that it allows bursty traffic if enough tokens are saved. Okay. Then after, bucket contain the packet, so bucket overflow when it is full. And here on the other side, or we can say in the token bucket, we can say bucket contains token, so token accumulate when it is not used. Okay, rather than overflow, it will accumulate the tokens. Okay, if the bucket is full, extra packets are discard in leaky bucket algorithm concept. But if the bucket is full, extra tokens are discarded when it comes to token token bucket algorithm. Here we can say that the traffic shapes where smooth flow is required. Okay, and here the traffic shape and policies where burst are accepted. Okay, here the in the other side, means in the leaky bucket algorithm, we can say output is constant and strictly controlled. And when it comes to token bucket, the output can be variable depending on the token availability. Okay, so remember the points which we have discussed here. Okay, moving to the next, IPv4 classful addressing. So IPv4 classful addressing is a early scheme for organizing and allocating internet protocol addresses in IPv4 system. In this approach, we can say the 32-bit address space is divided into 5 classes. Okay, that is A, B, C, D and E, based on the value of leading bits, and each class determine how the address is split between the network and the host portion. So here, classful addressing is the original method used in IPv4 to divide the IP address space into fixed class. This method was used before classless inter-domain routing was introduced. Okay, classless inter-domain routing, CIDR, was introduced. In classful addressing, the entire IPv4 address range from 0.0.0.0 to 255.255.255.255 was divided into 5 class, that is A, B, C, D and E. So the structure of IPv4 address, we can say that the IPv4 address is 32-bit divided into 4 octant. Okay, that is A, B, C, D. So each was having 8-bit. In classful addressing, the first few bits of first octant determines the class. Okay, so here the classes of IPv4 address, the first class is A. The leading bit pattern is 0, and the first octant range is 0 to 127. Its network bit is 8. Its host bit is 24. Number of network is 2 raised to 7, which is 128. Host per network is 2 raised to 24 minus 2. Default subnet for class A is 255.0.0.0. Okay, and this class A, this is generally used in very large organizations or government network. When it comes to class B, the leading bit pattern is 10. Its octant range is 128 to 191. Network bit is 16. Host bit is also 16. Number of network in class B is 2 raised to 14. Host per network is 2 raised to 16. Default subnet mask is 255.255.0.0, and the usage is it is used in medium organizations or universities. When it comes to class C, the leading bit is 110. Okay, octant is 190. Octant range is 190. Octet range is 192 to 223. Network is 24 network bit. Host bit is 8. Number of networks is 2 raised to 21. Host per network is 2 raised to 8 minus 2. The subnet mask which is used is 255.255.255.0, which is usually used for small networks or small companies. Class D and E, we can say class D, this is used for multicasting. Class E is used for experimental. So here when it comes to class D, the leading bit pattern is 1110, and the octet range is 2242 to 239. Okay, there is no network or host division in this area. And when it comes to class E, it is about triple 4 times 1 is the leading bit pattern, and the octet range is 240 to 255. The majorly these kind of used in normal, this is not used in normal network. Okay, so here classful addressing is an IPv4 addressing method that divide the entire D and E based on the first few bits of the addresses. Each class has a starting bits are this, these are the classes, these are the address range, and these are the networks. Okay, which use of IP addresses, we can say how many networks and hosts are possible with that class, that can be identified. The default subnet mask, that device used to interpret network versus the host part. The range of the address allocated for various purposes, that also can be identified by understanding or by seeing the address range. Okay, so here devices and routers can automatically distinguish the classes of IP address and apply the proper subnet mask without explicit configuration. Okay, so here we winding up the session. Okay, so the topic which we learn here are the design issues of network, store and forward packet switching, what it is mean, right? What does it mean? Optimality principle. Then after Dijkstrau or Dijkstrau algorithm, shortest path and flooding algorithm. Okay, then flooding in routing. Flooding differs from adaptive routing algorithm. Working of distance vector routing algorithm. Then the limitations and solutions for count to infinity problem in distance vector routing. Then after the steps that are performed in link state routing. Then after the concept of link state packets. Okay, then after why is traffic management required in the modern network. Differentiate the congestion control and flow control. What is admission control protocol? What is load shedding in network? What is RED algorithm, random early detection algorithm? What are chalk packet? What is ECN? And explain IPv4 classful algorithm. So these are the different topics that we have learned or what we have discussed here. Okay, so I hope the content was very clear for everyone. If it is not clear, if any concept you missed, or if any concept is very difficult you to understand, I request please message me, or you can ask. Okay, accordingly we can discuss on this area. Okay, now one more session will be there for transport layer. and application layer. Again, I am reminding, whatever the doubts you have, you can clear it, you can ask it, okay, in the next session also, so that you will come to know what how to clear, or what are the points that you have to write when it comes to some specific areas. Okay, so I hope, again, it's very clear for everyone, the concepts are clear. Okay, God bless. Thank you.